Hello students, I welcome all of you in our fourth chapter, Effects of Electric Currents. Today we will discuss the magnetic field produced by a current through a circular loop. In a circular loop, when current is flowing in the circular loop, how the magnetic lines of forces are aligned in that surrounding and what effects we have seen. This topic we will discuss today. After that, the magnetic field due to current in solenoid. Current in the solenoid. This is the different types of shapes are there. Just like slinky, which is used in telephone cable. So the solenoid is there, and the magnetic field due to the current we have to find out. After that, force is acting on a current carrying conductor. Force is acting on a current carrying conductor. This topic also we have to discuss, and if time remains we will discuss the Fleming's left hand rule, which is not mentioned here, but we will discuss those things. So 4 topics we will discuss today's lesson. So we have to start. The first one, the magnetic field produced by the current. The magnetic field is produced by the current when it is passing through the circular loop. We have already seen that when the current is passed in a straight conductor, we can see that there is a magnetic field produced around a current carrying conductor. Here is a circular loop. Instead of a straight conductor, we have to use a circular conductor. That means it is circular loop is there, conductor loop is there. Here is a loop. Okay. So first we have to see which are the components in our electric circuit. In electric circuit, the main component here we have used is cell. The cell which can does all this thing, and that means a current is passing through this electrical circuit. After that, here is a conductor loop is there. Circular conductor loop is there. Here is a cardboard. The cardboard we can use. We have just inserted a copper wire, that is insulating copper wire is passing through the cardboard. So we can find out the type of magnetic lines of forces are there. The magnetic lines of forces which are not visionary, and that's why we can experience these lines of force by using different substances are there, that magnetic substances you have to use for that. And here is a rheostat is there. Rheostat for a purpose, that means changing of a resistance, and changing of a resistance we can control the how much amount of electric current flowing in the circuit. Okay, so this component, this instrument is used to change the electric current, and this instrument ammeter is used to see, to vary. We can by naked eye we cannot analyze that the how much amount of current is passing through it. So by using ammeter we can easily find out how much amount of electric current it is greater amount or a less amount. Okay, so this instrument is used to change the electric current. This instrument is used to measure the how much amount of electric current is there, and the cell is used to provide an energy source to carry out the electric charge from one point to another. And in this way, the positive terminal is there, so the current is passing through in such like that in the loop, conductor loop, and after that it comes towards the negative terminal and electric circuit completes. So what you have to do here, we can easily see that if we see the magnetic lines of force, we can already see in the last period that when current is passing through the conductor, there is magnetic lines, magnetic force, magnetic field is created near it. Magnetic field is created near it, and in a circular loop it is just like a concentric circle. Okay, there are 2 points P and Q. here only we have taken these 2 points only, okay, this point and this point. There we can easily find that there are number of points on the loop and they can create such type of a magnetic lines of a forces. These magnetic lines, this magnetic field is surrounded by the circular loop, okay. Every point can be created such type of a magnetic lines are there, but only for a representative point of view we can choose only these 2 points, okay. So these are the concentric circles are there. In that circle we can find out the magnetic lines. Here is the magnetic lines of forces, okay. Magnetic lines of forces are there. So from this point to this point, if we coming from left to right, we have found that we have to find those things that there are these circles are their radius is increasing. Their radius is increasing. That means circle is bigger and bigger and bigger. Okay. And at the center, at this point, we can see there is a straight line. There is straight line. Why it became straight line? Why it is straight line? Because the size of the circle, the radius is such like that there is much bigger than we expect. So that in both this point and this point, these are the center. These are the center of these 2 points P and Q, and due to this point P and Q, we can find out the magnetic field near it. The magnetic field near it, and it is in the form of a circle. It is in the form of a circle. So radius changes. These are the concentric circles. These are the concentric circle, and its radius changes automatically. It becomes more bigger and bigger and bigger. Okay. So that at the center of these 2 points, that means at a middle portion, we can find that the lines of forces are in the straight line. So in this way, in a conductor loop, when you carrying out electric current through a conductor loop is there, the nature of a magnetic field is such like that. These are the circular concentric circles which the lines of forces are aligned. They are aligned. They are situated and such like that. Okay. So after that, the cardboard is used. The main purpose of it to find out how the magnetic lines of forces are situated. How the magnetic lines of forces are situated. Okay. So we can find out the direction of current is such like that. Okay. The direction of current is such like that. So by using right hand thumb rule, we can easily find the direction of a magnetic field. Direction of a magnetic field is such like that. Direction of a magnetic field. Okay. The direction of magnetic field. The direction of current is already provided to you, and from that we can find out the direction of a magnetic field. So we have to check whether this point, how the direction of magnetic field changes or remains continuous or remains static, and such like that. From here also we can see that the magnetic lines of forces, the magnetic field, the direction of a magnetic field we can easily find out by using Fleming's right hand rule. Okay. So after that there is one point I want to mention here: the intensity of a magnetic field. The intensity of a magnetic field. So intensity depends upon the electric current. Okay. If the current passing in the circuit is weak, we can see the concentric circles are very close to each other, and a very weak magnetic field we can find out. Okay. Very weak magnetic field we can find out surrounding to that point, to that every point on the circular loop. That means conductor loop is there. So if the number of loops are there, we increase the intensity, if we increase the intensity, that means current, the amount of current flowing in the conductor loop is increases, then we can easily find out the intensity of a magnetic field also increases. Intensity of the magnetic field also increases. So if we, instead of one turn, if we made a number of turns, if we made, instead of this one turn, if we made number of turns, a chain, number of turns, if we wound a copper wire, and number of turns are there. So one turn it gives if we increase the number of turns, automatically the magnetic intensity of magnetic field also increases by n times. Okay, if n number of turns are 1, then magnetic field the intensity is 1. Okay, but the number of times the turns increases, loops increases, these loops, the number of loops increases, then automatically we can see that the magnetic field intensity of magnetic field increases n number of times. That means n number of loops, that magnetic field also increases by n number of times. So this topic we have to already discuss. After that we have to find magnetic field due to current in solenoid. For that we will first we have to draw a diagram related with it. On a page number 54 we have provided the diagram such like that. There are number of loops. Okay, these are the loops, and its end is connected to, and its end is connected to cell. Okay, here is a key, here is a key, and here is a key, and they have shown that the number of lines and such like that. Okay, and they are shown in such like that. Okay. So here the solenoid is such a type of a construction of a wire which is wound on a circular loop, and these end terminals are connected to cell and the key. After that we can realize that the magnetic lines of forces are such like that. They are such like that. Okay, they are already shown in our book. Okay, here is S and here is N terminal. So for a bar magnet, we can see that in a bar magnet the lines of forces for a bar magnet, lines of forces are such like that. Okay, the same thing is happen here. The solenoid means the number of turns are wounded. Number of turns are wounded on any rod. We have taken a rod and we have to wound a copper wire is there, and this type of construction is called as a solenoid. This is called a solenoid. So the function of a solenoid is same that of a bar magnet. Here is bar magnet is there, and in a bar magnet the lines of forces are such like that. They are elliptical sense of semi-elliptical. Okay, and same thing happen here. If we connected a source is there, that means a cell is there, here is key, and after passing an electric current through the solenoid, we can easily find the number of lines which is that means a magnetic field which is produced there due to the electric current is such like such like a bar magnet. In a bar magnet, lines of forces are such like that, and the same thing, these are the magnetic lines. These are magnetic lines. Okay, magnetic lines are there, and the current is passing. The current is passing through in such like that. Okay, the current is passing through in such like that. So, in a bar magnet, the lines of forces are aligned such a way that in a same fashion, in a similar fashion, in a similar way, we can find out the number of lines produced. The number of lines are produced when current is passing through the conductor. Current is passing through the conductor. That means a number of loops. That is a solenoid. The construction of a number of loops is called a solenoid, and when current is passing through the solenoid, we can easily found that the magnetic field is produced there, or the magnetic field is produced there due to the current is flowing in this conductor is in a similar fashion, just like the bar magnet. In a bar magnet, the lines of forces, that means the magnetic field, are such a alignment is such like that. The magnetic lines are such like that. N to S, S to N, and N to S. Okay. So in this way, we can find that the magnetic field due to current in a solenoid is such like that. Okay. The next thing is force acting. For that purpose, I have to draw a figure. And we will discuss what happened in that experiment. For that experiment, on page number 55, we can see that here is a stand. We have to adjust a horseshoe magnet. Here is horseshoe magnet. Okay. Magnet, in a horseshoe magnet, we can align a straight conductor which is passing through it. Okay, and the electric current is passing through it. So another here. So another stand is there, and from another stand which is used here is a stand. Okay, and this stand, this is stand. Okay, and this stand hold the terminal A and B. Here is cell, and this is first stand, this is second stand, and this stand holds the cable, that means a conductor AB, which is connected to the cell. Here is cell, here is key, and here is a connector. Okay, here is a connection. When the electric current is passed through this wire, that is a conductor, we can experience that. So before, when key is open, and the situation is such like that, when current is not flowing in the electric circuit, at that situation, this cable, that the cable means that the conductor, this conducting wire remains as it is. This conducting wire is passing through the horseshoe magnet. It's such like that. Here is horseshoe magnet, and this wire, this AB terminal is adjusted. We have to adjust it such like that, and after that we can find out that when current is not passing through it, we can see that this cable remains as it is. That means the conducting wire is such like that. There is no force is acting on the wire. When force is acting on wire, when we close the key and the electric current is passing through it, and we can say that when the electric current is passing through it, we can say that it bends toward either side, this side. Okay, it bends towards either side. Okay, these conducting wire bends towards this side. Why it bends towards this side? Because this wire carrying a electric current. Okay, when it carries a electric current, there should be magnetic field is related with that current carrying conductor. That means this cable. Okay, it also possesses a magnetic field, and here is horseshoe magnet. So these two polar, that means N or S terminal is there, and we know that there is attraction between opposite charges, opposite poles, and repulsion between similar poles. Okay, so that the magnetic field near the current carrying conductor and the horseshoe magnet, if their polarities are same, they reflect each other, and if their polarities are opposite, they attract each other. That means it bends towards left hand side is due to there is attraction between this N pole or N pole, whatever it may be, whether it is N or whether it is S pole. So the force which attracts the horseshoe magnet having attract this conducting wire, current carrying conducting wire. Why it is attract towards the horseshoe magnet for one either side? It is due to when current is flowing in the conductor, it produces a magnetic field. Okay, when current is passing through the conductor, there is magnetic field is there is polarity is there, whether it is N pole or S pole, and according to this current carrying conductor bends or attracts. It attracts towards either side, whether it this side or this side. Okay, from top to bottom, from bottom to top, when current is passing through from bottom to top, it bends towards this left side. Okay, from this side, and when we change the polarity of the cell, that means negative terminal becomes a positive and positive terminals become negative. So the direction of current reverses in electric circuit. The direction of current reverses, so that current is passing from, instead of bottom to top to bottom, electric current is passing from top to bottom. At that time we can see that the current carrying conductor, it bends towards this side. Okay, in short, we can say that when reversing current, the direction of the current carrying conductor attracts in either side, whether left side or right side. It depends upon the direction of current. Flows. Here we can see that that means some sort of force is there. Okay, first one is due to the electric current. Magnetic field is produced, and due to magnetic field is production of a magnetic field, there is some sort of a force acting, mechanical force is acting on a conductor. So force is there, electric current is there, and magnetic field is there. They are mutually perpendicular to each other. And these things we have to study in that experiment. That is, force is acting on a conductor. That means force is acting on a conductor. When current carrying conductor is placed in magnetic field, it experiences a force. It experiences a force, whether it is either side, this side or this side. Okay, this depends upon the direction of electric current. And why it bends towards either side? Because there is a magnetic field is related with that electric current carrying conductor. When current is passing through the conductor, there is a magnetic field is related with. They are mutually perpendicular to each other. That means electric current and magnetic field are perpendicular to each other, and these are the two parameters. One parameter is electric current in a conductor when passing through the conductor. Due to that, magnetic field is produced, which is mutually perpendicular to each other, and due to that, it experiences a force. It experiences a force when it is placed in a magnetic field, another magnetic field. When this current carrying conductor is placed in another magnetic field, it can experience a force, and this force why? When two magnets are come in contact with each other, opposite polarity attract each other. Okay, opposite polarity attract each other, and similar polarities are repel each other, and this phenomenon we can see in this activity. So that from that we can conclude. Here we to conclude this lesson. But in the next lesson we can see Fleming's left-hand rule, which is depend upon the three parameter: electric current is there, magnetic field is there, and force acting on the current carrying conductor. Okay, I can stop.